so far. So we've done spheres. X minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to r squared. We've done ellipsoids. X minus x naught squared over a squared plus y minus y naught squared over b squared plus z minus z naught squared over c squared is equal to 1. And then we did a couple of paraboloids. Elliptic paraboloid. So I think I was z is equal to, and I don't know if I did the shifting and then the changing things, but we can account for those things also. I'll just put a x minus x naught squared plus b y minus y naught squared. So that's a paraboloid that has cross sections that look like ellipses. I don't know, I guess I should have divided by a squared and b squared. That's probably how it looks like. Actually, let me do that, sorry. I think that looks more elliptical. But the word elliptical is inspired by horizontal cut of the surface, and then the result that you would get would be an ellipse. And then the last one we did was hyperbolic paraboloid. And these are just generic equations. So there might be a different minus sign somewhere, or the form might look slightly different, but it's the same idea. And what is going to be important for you is to be able to look at a random equation and then be able to tell what kind of surface you should expect from that. And you can start by looking at the differences between these equations, these things. So the way I like to draw this is or one way to think about drawing it is you have parabolas that are opening up if you go one way, and then you have parabolas that are opening down if you go another way, and then that ends up looking like a saddle. And we saw by some graphic last time that the cross-sectional cuts of these things kind of look like hyperbolas. not kind of look like, they are hyperbolas. Yeah. I don't know. I think I was trying to make it look like an ellipse. Don't just accept it. I added there because I said so. No, let's do an example of what I mean by that, and we'll take a look at why it's called elliptical. And so I did the same thing over here. I added a squared over b squared and stuff. But let's take a look at y, and I'll give you some examples. So let's take a look at, before we move on, there's 3 more I think that we should know. 3, 4, I don't know. There's 3. There's 3 more that we should take a look at in detail. Actually, this particular section talks about cylinders too, but we talked about cylinders already, remember? If I have an x squared plus y squared is equal to 1, that's a circle, right? But in 3 dimensions, it's a cylinder. Yeah, some people might call it circular cylinder. Anyways, well, we might take a look at some of that later. It's too late. I'm going to do one anyways. So let's take a look. Z is equal to, I'll keep it simple with just an x squared over maybe 4 plus y squared over 9, something like that. And more likely you'll see these things where these are, oh, never mind. Let's just take a look at what this is supposed to look like. So the z is not, so a couple of key things to look for is that the z is not squared. The x squared and y squared, x and y are both squared. And they're both positive. They both have the same sign. They're both positive. So you should already be thinking that this is sort of some sort of paraboloid. And it's an elliptical paraboloid because they both have the same sign. And it would be, the cross sections will be whatever the cross sections are. Anyways, so what people do sometimes is they try to imagine a graph, so somebody who can view things in 2 dimensions or can draw, you should be able to draw things in 2 dimensions. Now, drawing things in 3 dimensions might be a little bit difficult, but if you try to put those ideas together, you should come up with a 3-dimensional model of this thing. So here are some of the things to try to do to try to be able to visualize this. So we could take some cross-sectional cuts. And we'll cut it with, let's start off by cutting it with the coordinate planes. Maybe cut it with x is equal to 0 and y is equal to 0 and z is equal to 0, just to imagine how this is going to look like. So let's let x equal to 0. What's x is equal to 0 again? If I were to graph that in 3 dimensions, I'd just say x is equal to 0 as a graph. What's that going to look like? It's a what? What? Vertical line? The YZ plane. It's a plane. It's a whole plane, and it's the YZ plane. So when you say x is equal to 0, we're thinking about the YZ plane. Now, if I let x equal to 0 here, I get z is equal to, x is equal to 0, so this is just y squared over 9. So that looks like a fairly wide parabola on the YZ plane. So if I were to take a look at this on the YZ plane, I'd have some sort of parabola. Now let's take a look at this on the y is equal to 0. So when y is equal to 0, I get z is equal to x squared over 4, and y is equal to 0, so that whole term is gone. And similarly, I would have a parabola over here. All right, so let's throw another one. Let's say what happens on the xy plane. And you'll see this quite a bit, and you'll have to be able to deal with this. When z is equal to 0, I have 0 is equal to x squared over 4 plus y squared over 4, which is 9, which is what? What is this? What points x and y can I put in here to satisfy this equation? 0, 0 is the only one point that I can put out of all the points, out of all the infinite number of points on the xy plane. 0, 0 is the only one I can put in there for this to be true. So that means on the xy plane, all I have that represents this graph is a point. So those are generally called cross-sectional cuts, slices, or whatever. Now, in general, especially when we start studying functions of several variables in Chapter 14, we tend to look at these things called level curves by setting z equal to not just 0, but z equal to a bunch of numbers. Of course, we can let x and y equal to a bunch of numbers as well, but the idea of a level curve is to cut the surface with a horizontal plane, a plane parallel to the xy plane, and to see what your result is. We saw some of that yesterday in the graphics again, but we'll formalize this idea of a level curve when we get into Chapter 14. Level curve is by setting z equal to some constant. So we'll take a look at when, say, z is equal to 1. What do you get? You get 1 is equal to x squared over 4 plus y squared over 9. And this is the reason why it's called an elliptic paraboloid, because a level curve of this. Now, this is exactly on the xy plane, but I'm going to put xy on my axis. So this is called an elliptical paraboloid because these level curve cuts are going to be ellipses. So 3 and 4. Oops, let's call it 2 and 3. And this is why you needed to know how to graph some of those conic sections back in Chapter 10. Are you guys experts at that yet? I should have given you guys a quiz on that. Anyways, the major axis here is the y-axis and cuts at positive and negative 3. And then the minor axis is the x-axis. It cuts at positive and negative 2. So we can go on and do a couple more of these. So it's going to be slightly bigger. I don't know exactly what the intersections are, but you can find it. And then one thing to notice is that if you were to draw, try to draw a level curve when z is equal to negative 2, we're going to get negative 2 is equal to x squared over 4 plus y squared over 9. And what would that yield? Any ideas? Imaginary numbers. Nothing. So that means this surface, whatever the surface is, if you try to cut it with a plane z is equal to negative 2 under the xy plane, you're not going to get anything, which means this surface does not exist down there. Yeah? I don't know. What should it be? Okay. Any ideas? Because when x is equal to 0, the only way this will work is that if y is positive and negative 3, right? And when y is equal to 0 on the x-axis, the only way this would equal to 1 is if it's positive and negative 2. I don't know. I think it's right. Should we graph it? Well, but this is 3, 0 or 0, 3, right? I don't know. I think it's right. X squared divided by 4 plus y squared divided by 9. It looks 3 and 2. Yeah. All right. So in any case, what this is saying is that it doesn't actually, any negative number we put in here means that we're not going to, because the right-hand side is always positive, it's going to be squared. We're not going to have a true equation, which means nothing, this surface is not going to exist below the xy plane. At the xy plane, you only have a dot, and below it will not exist. All right, so let's see if we can put these ideas together in some sort of a drawing, a three-dimensional drawing. And this is where that VR would have been nice. But let's see. According to what we found on the, when x is equal to 0 on the y z plane, we got parabolas that are wide. On the x z plane, we're going to get parabolas that are a little bit less wide. On the xy plane, we got a dot. And if we go up one level, we're going to get an ellipse. If we go up another level, we're going to get another ellipse. And so as we start putting these graphs together, we begin to see what's really happening here, right? And then our result will be basically a bowl that we would call a paraboloid. Okay? Any questions? All right, we could do the same analysis in using or viewing, trying to view the hyperbolic paraboloid, but we could just, you guys can look at that. All right, let's examine some more shapes. So let's take a look at an example where we have a z squared is equal to x squared plus y squared. Wait, is this the Is this a paraboloid? Why is this not a paraboloid? Because the z is squared, right? In the paraboloid, the z was not squared. So in this case, the z is squared, so it makes it not a paraboloid. So what is it? Well, let's see. Let's do what we did by looking at some of the cuts and curves. This is going to be kind of weird. Let's see. Let's let x equal to 0 and see what happens. This is on the xz plane, right? No, the yz plane, sorry. It is on the yz plane. So z squared is equal to y squared. What is that? What is z's? What? A line? It'll be two lines. So it's a line, but there's actually two of them. Z is equal to y, z is equal to negative y. You know, plus and minus, the square root, plus stuff like that. So anyway, so we get this. Weird. Let's let y equal to 0. Well, you're essentially going to get the same thing, right? So on the xz plane, you're going to get an x. Let z equal to 0. You think you're going to get another x here? 0 is equal to x squared plus y squared. What? What is this again? It's just a dot, point at the origin. All right? Yeah, so now if we do the level curves, when we let z equal to stuff, we let z equal to 0 already, so let's let z equal to 1. You get 1 is equal to x squared plus y squared, okay. Z is equal to negative 1. What are you going to get? Plus y squared. So it turns out that whether you have 1 or negative 1, you're going to get the circle of radius 1. And when you let z equal to 2, you're going to get another circle with some larger radius, radius 2. So yeah, can you picture this? I mean, Evan already said it. So along the x, or along the yz plane, you're going to get this x. Along the xz plane, you're going to get another x. Well, that's just going to get confusing. Why don't I just say it's going to be so these are cones. Cones. Okay, you see the cuts, the x cuts, the x cuts. Another x cut would be, let's see, it would be somewhere over here like this. And then you see the circles. Okay? Now remember, these are the general forms of this. So if I move this off center, it'll be x minus x naught quantity squared. And then we can multiply or divide it by some constant that would make this more elliptical instead of circular. More like an elliptical cone instead of a circular cone. Okay? Now, so that's interesting. Let's take a look at this one. I don't know, maybe we should look at these two. Now, they come in different forms, and so you may see them a little bit differently in the book or wherever you might run into them. I think the book presents the second one with negative x squared minus y squared plus z squared is equal to positive 1, just to keep consistent with the positive constant on the other side. But anyways, this is not quite a cone anymore, because you have an extra constant laying around. It's not quite an ellipsoid, because an ellipsoid has positives for all of them. So what do you think?
No, if z is 0, then it's undefined.
It looks like it would be undefined when x and y and z are equal to 0.
Exactly.
All right, let's take a look at the first one. Let's do our cuts and stuff.
I mean, on the right hand one, it's undefined.
Well, let's go through this and systematically, since we've been kind of establishing some ways to try to approach these things. For the first one, let's let x equal to 0, and we have y squared minus z squared is equal to 1. What is that? I know I didn't spend too much time on this, but it's a hyperbola. It's a hyperbola, and the way I would check which way it's opening is that if y was equal to 0, then I have a negative number equal to a positive 1. So y is equal to 0, that's the z-axis, is not going to exist. But if z was equal to 0, I have y is equal to positive and negative 1. So I know that the hyperbola is going to be hitting at the 1s on the y, and it will just be opening up this way. So y equals 0 will be the same thing. And when z is equal to 0, this is x squared plus y squared is equal to 1.
So this one actually is another one.
Okay, we'll find some more cuts. Like maybe z is equal to 1. If z is equal to 1, I get x squared plus y squared is equal to, z is equal to 1, this is negative 1 brought over to the other side. Does that become 2? So that's another circle, slightly bigger. How about if we put negative 1? We'll get the same thing. Okay? So if you haven't got a visual yet, silo. I don't know. Nuclear power plant?
That's That's a cooling tower.
A cooling tower.
And then for 1, the constant in all this determines the minimum radius that it reaches.
Okay. All right, let's take a look at the other one, just for comparison's sake. X is equal to 0. I'm going to get, what am I going to get? Which equation should we, well, let's use this equation over here. X is equal to 0. We got y squared minus z squared is equal to -1. Oh, that's equal to -1. So in terms of hyperbolas and the conic sections, we would prefer to have the other side equal to 1, which is probably why a lot of books use this equation. And so that would just switch the order of this. You get z squared minus y squared is equal to +1. And I think that would be a hyperbola opening up and down along the z-axis. So the same thing with x. On the xz plane. And when z is equal to 0, we'll see that x squared plus y squared is equal to -1. So there's no image for that, which means this thing doesn't exist on the xy plane. Might seem drastically different, but let's try more cuts like z is equal to 1. When z is equal to 1, I'm going to get x squared plus y squared is equal to 0, and that's just a dot. When z is equal to -1, we're going to get the same thing. You see that z is squared, so it's like a mirror image. Whatever happens on top is happening. Whatever happens above the xy plane, the same thing is going to happen below the xy plane. And so z is equal to 2. I'm going to get x squared plus y squared minus 4. Bring the 4 over to the other side. We're going to get a 3. So now we're going to get a circle. Radius, whatever, square root of 3. This is a little harder to visualize because we got like an empty space around 0 around the xy plane, but can you picture it? Yes, it is. Well, let's see. Yeah, let's put the bowls in. I'll put the axis. So this is what we get. These are called hyperboloids. The first one is called a hyperboloid. Oops, hyperboloid. Hyperboloid. Hyperboloid of one sheet. And guess what the next one's called? Hyperboloid of 2 sheets. Okay? So, those are the quadratic surfaces. You got the sphere, the ellipsoid, the paraboloids. There's a hyperbolic paraboloid and an elliptic paraboloid. There's the cone, and there's the hyperboloids of 1 sheet and 2 sheets. Now, as I talked about them, I gave them the example where they have these representatives. Something's going on. They look like these equations, but if there's a slight change in any of these equations, then we're going to have to somehow transform our graph by either shifting it or doing some sideways reflection or something like that. So it's important to know the basic formulas attached to the picture of the graph, and it would be good if you can attach that to the name just so you can converse. But once you know the basic ideas of the equation and how it's related, then you can start messing around with the slight, minute changes that might change the form, the look, the shape. Not the big shape, but the detailed shape of the graph. So let's take a look at an example. And now this might seem to come out of nowhere, but it actually is something. What is this a graph of? Cone. So we saw the graph of the cone, right? Does it look exactly like that, or what? Which half? The top half. So this is a cone, but this is only the top half of the cone. All right? What do you think this looks like? So this is a paraboloid. Which kind of paraboloid? Elliptical or circular. It's a circular paraboloid, elliptical or paraboloid, but you know the cross-sectional cuts are going to be circles because there's no difference in the coefficients here. So this is a circular paraboloid. Opening up which way? In the positive x. So it's opening up not just in the x direction, but actually in the positive x. So maybe I should erase this little bit over here. So there's a paraboloid opening up in the positive x direction. Right? Looks like a paraboloid, except instead of z is equal to x squared plus y squared, it says x is equal to that. So we have to make the adjustments. How about this one? Hyperboloid of 1 sheet or 2 sheets? 2 sheets, right? Right? Is it? 1 sheet. How can you tell what's the difference between a hyperboloid of 1 sheet versus a hyperboloid of 2 sheets?
How many
Which and how many values are negative, right? So if we go with a notation where the right hand side, if it's going to be a constant, it's just going to be a positive 1, then the hyperboloid of 1 sheet or 2 sheets have 2 negative numbers or 2 negative variables, and then the other one is positive, and then the constant is positive. The hyperboloid of 1 sheet has 2 positive variables, 1 negative, and then the right-hand side is positive. Okay, so I think it follows this form. We got x and the z are both positive. The y is negative, so there's only 1 negative, while the right-hand side, the constant, is a positive constant. So this is 1 sheet. Maybe I should label these. This is a cone. This is an elliptical. I'll put elliptical, but circular. And then this one is a hyperboloid of 1 sheet. And it's opening up which way? Along the y. So this is the y-axis. Then if you want, you can be opaque or semi-transparent. And you know it's opening it up on the y-axis because that's the only variable that has a different sign from the other 2. Okay? Questions? My mouse keeps going. Yes?
That top one was negative.
This one? Yeah. You can put negative z or negative in front of the square root. And then we'll be pointing to the bottom. Oh, why don't I just make a real example out of this? We change this equation slightly and say 3 minus that. What do you think is going to happen there? Shift. So it'll go up by 3 units. So my cone would have been shifted up 3 units, upside down. So once you get the feel for all these surfaces, then you do the proper shifts and the change in variables to make it go sideways or downward or along the x or along the y. Okay? Yeah, because y is the only one with a different sign than the other ones. And if we look at our,
Sorry, if it were negative x plus y, then it would just be like that.
well, it depends on what the z is. So if it was negative x plus y plus z, then it would open up along the x. Yes. So if you look at the templates that we have here, the z is the one with the different sign from the x and the y. The z is the one with a different sign from the x and the y. And so this is opening up along the z. Okay? What page is that? 830. So page 830 in your textbook has a nice one-page summary of all the quadric surfaces that you should get to know. All right. Now let me show you.
Sorry,
No, yes, yes.
in the book, they're all over like a squared, b squared.
Yeah. I tried to squeeze that in over here to make it look more elliptical. But if a and b are equal to 1, then they're the simplest you can make it. But if they're not equal to 1, then these things, like in these cones, that just means instead of having circles, you'll have ellipses. And then likewise with the hyperboloids, instead of circles over here, you would have ellipses. Yeah.
How do you determine the amount of sheets? Is it just setting values? Is that the only way to determine?
Sheets for these two?
Yeah.
Yeah, so the amount of sheets will just be dependent on which is negative. Is it the two variables that are negative or the one variable that's negative? So if two variables are negative, then it's 2 sheets. If one variable, that's provided that your right-hand side's positive, which is why I think a lot of textbooks and a lot of people that present this, they always like to have this as positive 1 instead of having it negative 1 like I did. Right? So, yeah, when I was at UCSC, I had index cards of the equations, the graph, and the name of these things. And then I had a small group that I would deal with, and so I would just give them a little oral quiz that they have to answer like 5 questions correctly. I show them either an equation or a graph, and then they have to find, out of the other cards, they'd have to find the matching things. So over Math Jam this summer, one of the instructors was doing something like that with pre-calculus graphs. So if you guys are interested in doing that and playing that game, you should let me know. I have cards. We could, but I only have one set of cards. I was going to try to write a Python program that kind of randomized and shuffled and had you guys do the guess. But I was thinking maybe just having it as an actual quiz on Canvas or something. So here are the cards. Ellipsoid. You have to find the ellipsoid. And the graph of the ellipsoid. So you'd have this all turned around and you play a matching game. If you want. I wanted to show you this graphing program. Oh, there's a graph already. I wanted to show you this graphing program, and when you first run this graphing program, it has this function over here that's defined as z is equal to something. Now, that's something that we're going to study later on And in fact, some of the things that we're doing are kind of using this z is equal to something. And so we have the hyperbolic paraboloids or the elliptical paraboloids are in that kind of form. So let's take a look at graphing one of these things. So let's graph x squared plus, let's make it a little bit wider, 4y squared. And the not so nice thing about this is that you have to type it in like you know, the carets, and then it doesn't automatically typeset your equations nicely like the other program. But this will do the trick. So here's your paraboloid. And actually, I have this set so that it's maybe it's just a button somewhere. I have it set so it's it's transparent, but the default setting is that it's not transparent. So if I put a minus sign in between, that didn't happen. If I put a minus sign in between, then it's going to be that saddle, that hyperbolic paraboloid. And then with these, you can, well, you can do contour plots, trace menu, tools. Yeah, there's all kinds of other stuff that you can do here. But if you want to graph like one of those hyperboloids that we have, we can't get z by itself, right? We have the cone. If you look at just either the top or the bottom half of the cone, then we can get z by itself and just taking the square root. But the other ones, you can't get z by itself. And so with that, you have to use another graphing method over here called implicit surface. So I uncheck this right now. I uncheck this function, so I'll clear the graph. And then I'm going to go to the graph and say an implicit surface. And they have an example over here. And this example is, can you tell me what this example is? A graph of? It's a hyperboloid, right? You got x squared and y squared and z squared. They're all squared. X is positive, y is negative, z is positive. So this is going to be, there's two positives here and one negative, so this is going to be a one sheet. And so we'll ask it to graph, and it's opening along the y because y is the only one that has a different sign. All right, if we change this into, let me put a -2 here, so I'm essentially changing all the signs on the left-hand side, then it would be a paraboloid of two sheets. And these are the two sheets. Okay. So I encourage you to play around with this if you can, if you want. And if you have 3D glasses, I don't know, it's there. You can mess around with the view settings to get rid of the box and get rid of the axis if you want, and then just view. Yes? Would this be what? I think so. Yeah. All right. So, yeah, you guys can mess around with this. Oh, the other thing are cylinders. So let me do one more real quick. So you can graph multiple graphs. I have a surface graph. It says number 2 here, so there must be a number 1 somewhere. But I can call for another implicit surface, and then I can graph let me graph z is equal to sine x What do you think this is going to look like? So remember what happens when you have a graph, a three-dimensional surface that only has two variables. Do you remember what happens? Line? Okay. No, not filled in. Joe's making some motion with it. Yeah, kind of a plane of waves. What? What's that mean? So imagine your sine function on the xz plane and then just kind of stretching it out. So let's see if this is going to graph. Well, there's only a piece of it, but here's your wave, or a little bit of the wave, and then it's being stretched out. I should have hid the other graph. So higher frequency, right? Oh, it kind of became... I told you why this happens, right? Didn't I tell you about that? Yeah, well, it's interpolating according to the number of points you tell it. So this is a number of cubes in each direction. So if we want it to be finer, we make this larger, and then it becomes smoother. So it would normally take longer, but can we undo that?
Can you show it like what would be two-dimensional and so it's just
I would have more control with the other program than this one. You can, except I don't know how to do it off the top of my head. I've done it before, but I can't remember, and so. But it can be done. You can see it, you know, from the XY or the XZ plane and then being stretched out. All right, let's do 3.1 real quick. 13.1. So 13.1 is the beginning of vector valued function. And vector valued function is simply parametric equations put into a vector. So if you have those parametric equations, now we did parametric equations in two dimensions of x and y, but if we add a z to it, you got these parametric equations, and then you put them into a vector form like this, then you have a vector valued function. And what this does graphically is this is a curve in three-dimensional space. Now the simplest example is the combination of cosine theta, sine theta, or t, and t. So imagine this is a curve. You're tracing a curve out in 3 dimensions. And imagine the x and y going in a circle, right? Now, as your t increases, your z, because z is equal to t, is also going to increase. What is this going to look like? like a spring stretched out. So as you're going along the x and the y, your z is increasing. And so you have the most famous three-dimensional curve called the, anybody know what it's called? Spiral. Anybody know what it's called? It is a spiral. Helix. This is called a helix. A double helix would be two of these helices and connected with those. Any biology majors? Oh yeah, you're going to be studying that, huh? Genomes and... Anyways, this is really all there is to this section. The other kind of difficult part is trying to imagine these things in 3 dimensions, from 2 dimensions to 3 dimensions. But if you focus on 2 at a time, maybe like the first 2 components, the x and y components, and see what happens in a z, then you might see some interesting things happen. Tomorrow we're going to do calculus on them, on these vector-valued functions. And so we're off and running to this new chapter. See you guys tomorrow.